Imagine tuning your radio to a favorite station. How does the circuit know to pick out just that one signal from a sea of broadcasts? This precision isn't magic. It is the result of carefully designed resonant circuits that leverage fundamental mathematical relationships between three key parameters. Resonant frequency, quality factor or Q factor, and bandwidth are intrinsically connected through straightforward mathematical expressions that describe the behavior of a resonant circuit. Specifically, bandwidth is equal to the resonant frequency divided by the Q factor. Conversely, the Q factor is the resonant frequency divided by the bandwidth, illustrating their inverse proportionality. The fundamental link stems from their definitions. Resonant frequency is the specific frequency where the inductive and capacitive reactances in a circuit cancel each other out, leading to maximum current in series circuits or maximum voltage in parallel circuits. The Q factor, or quality factor, quantifies how much energy is stored in the reactive components compared to the energy dissipated by the resistive components per cycle, essentially measuring the sharpness of a circuit's resonance. A higher Q factor means less energy loss and a sharper, more selective response. Bandwidth, then, describes the range of frequencies around the resonant frequency where the circuit's power output is at least half of its maximum, often referred to as the -3 decibel points. This range directly reflects the sharpness or breadth of the resonant peak. Understanding these mathematical relationships allows engineers to precisely design and analyze frequency-selective circuits. For instance, if you need a narrow bandwidth to filter out specific frequencies in a communication system, you will design for a high Q factor. Conversely, a low Q factor would result in a wider bandwidth, useful for applications requiring a broader frequency response. You can directly manipulate the bandwidth by adjusting the resonant frequency or the Q factor, which are themselves determined by the circuit's resistance, inductance, and capacitance values. For example, reducing the series resistance in an RLC circuit increases its Q factor, thereby narrowing its bandwidth for a given resonant frequency. This intricate connection between frequency, quality, and spectral width is critical for everything from basic radio tuners to advanced radar systems. The half-power points or -3 decibel frequencies delineate the bandwidth and are essential metrics for characterizing filters and oscillators. These points are where the circuit's output power drops to 50% of its peak, providing a standardized measure of frequency selectivity. It is a powerful concept that allows engineers to predict and control the frequency response of countless electronic systems, ensuring optimal performance and signal integrity. Ultimately, the mathematical interdependence of resonant frequency, Q factor, and bandwidth provides the blueprint for engineering circuits that precisely interact with specific frequencies. Mastering these relationships enables the creation of highly efficient filters, stable oscillators, and reliable communication systems, giving you powerful control over how electrical signals are processed and managed.